Chapter L, inverse trig functions. We want to take a derivative. We're going to start first with the arc sine. And before we do that, we're going to do a little sketch of the sine here. So let's go ahead in the other direction. Okay, so this gives us the sine of x. This is x, this is y. And to get the inverse, what we would like to do is use our trick where we have y equals x line, and we're going to reflect this function about that line. And in that sense, we are swapping the x and y's, because inverse, you give me the y, I give you the x. Now this is a little tricky to do this because, see, this distance that we're from there, we have to go on the other side here. Remember, when you stand in front of a mirror and you want a reflection, your reflection is going to be the same distance on the other side. That's where the image is compared to where you are. So this would do something like this here. And you would continue, if you continue down there, you would continue, up here like that. All right, so let's go ahead and make this a little bit taller here, like this. Now we're really interested in this part because we got to be careful, because when we graph the inverse function like this, we can't have, for a given x, two values. So we're going to stop right there. And then if we come down here, we have something like this, we would stop and then not continue. So from here to there is very, very nice. And let's go ahead and mark this one as pi over 2. And see, this one here is a negative pi over 2. And when you have the negative pi over 2, what you're going to get here for your y, in other words, here, the sine of negative pi over 2 is -1. So this is going to be down -1. So if you came over here, for example, that's like a -1. Then if you go over to here, the sine of pi over 2 is going to be 1. So we could mark a 1, there. But now let's make a little chart. Say sine of minus pi over 2 is equal to -1, right? That's down here. And let's pick here the sine. Let's go ahead and take the sine of 0. That'll be equal to 0. And then the sine of pi over 2 is a +1. Is a +1. But now for the arc sine, if we have the inverse, we're going the other way, the arc sine of -1 has to get you the minus pi over 2. And then the arc sine of 0 has to get you back to 0. And the arc sine of +1, this would be +1, has to get you pi over 2. Now to help see this, we can go with a nice little unit circle like this, just to help us review our trig. And then here, this is going to be the place on the unit circle we're going to have the cosine. And then the sine is going to be here. So let's just take, for example, like 1. Say if we have an angle theta here, then the cosine of theta would be this horizontal piece, and this rise would be the sine. Okay, so it's a unit, go ahead and say unit circle. In other words, this is 1. The radius is 1. So here on this unit circle, if we want to look at the sine of negative pi over 2, that would be down here. So that angle would be negative pi over 2 would take you down here. And you can see down there, the sine, which is the vertical, is going to be a -1. In fact, this coordinate here would be 0 and -1. This coordinate here would be 1 and a 0. And this coordinate up here would be a 0 and a +1. Let's check another one. The sine is 0. If you collapse that angle to 0, then you would be, cosine would be 1, but the sine would be 0. And then if you go up here with pi over 2, your sine would be +1, your cosine would be 0. And if you want to go backwards, let's say if you put in here the +1 and you want the arc sine, you'll get then the pi over 2. And if you put in the 0, you'll get the 0. And if you put in here the -1, the -1 would be down here, sine of -1. You would get then negative pi over 2. So everything is fine. There's a 1-to-1 correspondence here because, we do our vertical test. We draw a line like this. You don't get two things crossing that line because see, that's dot, dot, dot. We took that out. So this is the restricted domain. So it would go from here. The restricted domain would go from here to there. Now that's a little tricky there because see, that would be going from, this is a 1. Pi over 2 is approximately 1.5. So the 1 would be there. This would be the -1. So that's a little tricky, and I'd like to see that at the same time as I see this unit circle to help give a bearing. So basically what we're looking at here is the arc sine restricted from a domain from -1 to +1. And then the arc sine will give us values minus pi over 2 to plus pi over 2. So in other words, like down here has to be your minus pi over 2. And then up here has to be your pi over 2. Now it's not the scale, but you get the idea. Okay, so what we would like to do is take the derivative, and now we're going to use our magic formula that we derived earlier, that if f of x is the function and g of y is the inverse function, then we have this formula. The derivative of the inverse function is 1 over the derivative of the function. So we have that prime. That means to take the derivative with respect to whatever the argument is. Now we derived that already, and we're going to now use it. So here, y equals f of x, and x equals g of y. So this is the inverse. So that means this would be the arc sine of y. And this is the regular function, which would be our sine of x. So now we're ready to do the calculation. So as we use this rule, we want the derivative of the g function, which is your arc sine. So the derivative, and this is going to be with respect to the argument, dy. And this is going to be the arc sine of y. That's going to be 1 over the derivative with respect to x of your f function, which is your sine of x. So this is d dx sine of x. Now we can do this one easily. The derivative of the sine is the cosine. And we can now relate this to the sine. We want to get the sine back in here. And all this will fall out in a second, you'll see. So this is plus or minus the square root of 1 minus sine squared of x. So the reason why we did that is because now this is y squared. You see, this is y squared because y is the sine of x. Now, is it plus or minus? Well, we're doing the derivative of the arc sine. The arc sine is this red one here, and you can see that the slope is always positive. We're never sloping down. We're going up, maybe not as much here. We're decreasing, then going more steep, but it's always plus. So therefore, d dy of the arc sine of y is 1 over the positive square root of 1 minus y squared. And now the last step is, since the y can be anything, could be a z, a u, we make it x and forget what we defined x to be above. So we basically write the final formula, the derivative with respect to x of the arc sine of x is equal to 1 over, this is kind of neat formula here, the square root of 1 minus x squared. That's far out, look at that. See, if we graph here 1 over the square root of 1 minus x squared, when, see, let's look at this, 1 over the square root of 1 minus x squared. All right, if we look at that, we see that when x is 0, we get 1, so we're here. So we're putting this, up here, and this is our x. So the y is this function. And then as x goes to 1, well, actually, when x is growing up, this is getting smaller. You're taking square root, and if you're dividing, you're getting bigger and bigger. So this is going to shoot up this way. And as you approach plus 1, you're going to shoot up to infinity. And then over on this side, as you approach minus 1, this will be symmetric. So on this side, you'll have something that does this, like a U there. Is that the answer? Well, let's think. When you're right at the middle here, the slope, it lines up with that y equals x. So the slope here is 1. So there's your 1. Then as you go here toward plus 1, look, this shoots up toward infinity. The slope here is infinite. That's what this is doing. And if you go the other way, the slope here is still positive, and it's actually getting more positive because this is infinite slope. See, that's 1, and this is getting more positive. And that's what this does. Isn't that amazing? So the trig functions, the arc sine is related to this 1 over square root function. Now let's look at the cosine. Cosine does something like this here if we sketch it like that. And on that side like that, cosine. So the cosine, if we were to work with the cosine and have this reflection going through here, we see that, so this one here will reflect doing something like this, going up here. As you go down there, then you're going to go up by the reflection. So here I have the cosine, say the cosine function. When x is equal to 0, you're at 1, and then you come down here. And when you look at the reflected line, we're going to reflect about this line. So if we look at this this is the y equals x line. Then when we do the reflection, you see that we're going to get the red. So as the blue line moves away from the green mirror, and it's the mirror, then we go in the opposite direction for the image. Now, if we want to look at, say, this piece, well, if we come here the same distance on this side to the other side, we would be there for that point. And then as we can look at this point, see, we would be there, and we can then kind of connect these, which would give us all the points that are the same distance on the other side. So you take any one like this, for example, point here, you go there, the reflection, the same distance on the other side. So we have a big problem here because, see, when you reflect this and get that red one and you do your vertical line, you're gonna have two values. It's not gonna work. So what we have done here is we have gone from 0 to pi. Now pi is roughly 3, so that's why you see a 3 down here, and a 2, and this is then a pi over 2, and a 1, and a 0. But the idea here is if you go from 0 to pi, and then you do your reflection here, this is going to reflect down there, and as you come to here, you come meet there, and if you keep going over like this, you keep going up. So this red function here is it's acceptable, because for every x you get one value. So this is the key here, is you want to go from 0 to pi. So when we do that, we can use our formula like we did before, the derivative with respect to y of the arc cosine of x, well, y, sorry. This is your inverse function here. And that's going to be equal to 1 over the derivative with respect to x of the cosine of x. So when we do this, we'll get 1 over a negative sine of x. And then when we use our trig identity, take the square root, we'll have, the minus or plus, a plus or a minus, the square root of 1 minus cosine squared of x. And then if we look at our slope, the slope of the inverse cosine is always going to be negative. So that means we want the negative solution. So that is d dy of the arc cosine of y is going to be, and this cosine of x, remember that's our y. That's our y. So this is y squared. So we'll have here a minus sign, 1 minus y squared. And then we then pick, instead of using y, we use x, and we get our formula, the derivative of the arc cosine of x is minus 1 over 1 minus x squared, like this. Now you refer to the book to see the arc cosine function, always negative, and then the derivative here, when we plot, remember our derivative that we obtained was minus 1 over the square root of 1 minus x squared. And we did, with a plus sign, we had a u that was going up. Now with the minus sign, the u is going to go the other way, starting here at a value of minus 1. And let's look at this. Always negative, starting out here with a negative infinity and then a negative 1. Starting over here, if you look at this, is way down at negative infinity, and then it's going to go here to be a negative 1. That would be the place right here for your slope. And then over here is negative infinity again. It goes to negative infinity, so it works out. So in a summary, for part 1, we show that the derivative of the arc sine of x is 1 over the square root of 1 minus x squared. And then 2, we show the derivative of the arc cosine of x is minus 1 over the square root of 1 minus x squared. And the next thing I'd like to do is find the derivative of the arctangent. So here we're going to let g of y be the arc tangent of y. Remember that we start with y equal the tangent of x, and then we let x equal the arc tangent of y, like we're going to go the other way. That's our setup. And then we just consider this as a g of y, and we consider this as an f of x, and then we use our formula that g prime of y is 1 over f prime of x. So that means the derivative of the arc tangent of y is 1 over the derivative of the tangent of x. This part here, in other words, dx of tangent of x is equal to the secant squared. So we're going to have, for the derivative of the arctangent, we're going to have 1 over the secant squared. Now we know that the secant squared is 1 plus the tangent squared. Now you could always derive that if you need to, that the cosine squared of x plus the sine squared x is equal to 1. You have to remember that the secant is 1 over the cosine. So when you divide both sides by the cosine squared, you get 1 plus the tangent squared equals the secant squared. And that's kind of easy to get from here. Just remember your secant is 1 over the cosine. So then this is nice because see, this is our y squared, because y is the tangent of x. So that means d dy of the arctangent of y is equal to 1 over 1 plus y squared. It's kind of nice. Similarity, like a variation of the other formulas. And then if we replace with x, we have d dx, arc tangent of x is 1 over 1 plus x squared. Now I'll refer you to the book, and the book, it has, this is the tangent, and the tangent behaves itself very, very nicely from minus pi over 2 to plus pi over 2. When you get the arctangent going the other way, when you do like your reflection, you're going to have this coming off the top, and reflecting this is going to be at the bottom. And then let's look at this function here in slope. The slope here is 1. And then as you go over to the right, the slope here is actually decreasing to 0. Decrease to 0. And here you are actually decreasing to 0 also. And there it is. And that is what the function, 1 over 1 plus x squared is going to give you. It's very nice. So this requires some time, some thinking, and reflection, and the book is going to help you do that. Notice that there is this very cool summary that's in the book where I have the here arcsine, arccosine, and arctangent, and I'm giving you their derivatives also, like in one picture, sort of as a review of what we have done and a visual. And I encourage you to spend some time studying this. And the book shows all the steps. So refer to the text, and remember that these are always put up at drphys.com, the website that goes with this particular YouTube channel, the Dr. Phys channel.